Hi guys, I'm Mr. Kane. Good to see you again.
Hi, I'm Mrs. Goswish. Nice to see you again too.
There's a message back there if you can read that. You'll get it. All right, so Unit 3, Atomic Theory and Protons, Neutrons, and Electrons. Is that how we read that?
What are the things in the upper right-hand corner? What does that mean? I mean, I get the symbol.
Yeah, see, this is a plus, and that's a 0, and that's a negative.
So does that mean the protons are positively charged? 0.
I'm positive about that, actually.
Positive? I'm positively positive. Well, all right, I get the positive by the protons.
I don't know anything here.
Does that mean no charge? Is that possible? There's an entity, a particle with no charge?
Cash only on that one.
Cash only, no charge. And the electron has a little negative sign.
No friends for the electron, too negative.
All right, Unit 3 goals, chemical foundations. You are going to be able to draw, describe, identify, and explain each of the historic models of the atom. That is going to include, but not limited to, Democritus, Aristotle, Plato, Dalton, Thomson, Rutherford, Chadwick, Millikan. You are also going to be able to determine the number of protons, electrons, and neutrons in atoms, ions, and isotopes.
Okay, so brief history of atomic theory. It turns out that atomic theory starts as far back as 600 BCE, before the Common Era, in India. But that's non-Western Civ, and here in the United States and in Europe, we tend to study Western Civ only, not non-Western, so we say it's as early as 400 BCE.
All right, now, Mr. Kane, I'm a little older than you, and I don't know all the new terminology. Tell me what BCE means again?
BCE is before Common Era.
Is that the new way of saying before Christ?
Yeah, it's the politically correct.
Oh, for the non-religious politically correct people.
It's still,
right.
We still use 0 as
the
get it. Origin. All right, so as early as 400 years before Christ, Democritus is a Greek philosopher scientist who comes up with this idea that if you start cutting things apart, you cut something in half, let's say you take an orange and you cut it in half, and you cut it in half again, and cut it in half again, you just keep cutting it in half. He comes up with this idea that at some point you're only going to be able to divide this orange so many times, and you're going to get to a piece of orange that's not divisible anymore. You can't cut it in half anymore. And he calls this idea atomos, which in Greek means indivisible. This is actually Democritus here. Basically what he is, he's the first person in the Western world that describes particles that are finitely divisible, which we now call atoms. I don't know why we call them atoms. I don't know why we call them atoms at all.
Using the terminology to your advantage, isn't that amazing?
It's absolutely amazing. The reason why you've probably never heard of Democritus, though, is because there were two other philosopher-scientists at the time called Aristotle and Plato.
Plato didn't play nice, did he?
No, they didn't. They wound up being better liked philosopher-scientists because some of their ideas were just better liked by the population. And they believed in the 4 core elements. They believed absolutely everything was made of earth, air, fire, and water. So if you divided things up into smaller pieces, eventually you'd get pieces of earth, air, fire, and water, not individual pieces of orange. Basically what this led to was something that we call alchemy. And Aristotle and Plato won out, and alchemy ruled for 2,000 years.
Wasn't alchemy the science of making gold?
Yeah, one of the tricks to alchemy was they were trying to discover how to make gold out of base metals like lead. We fast forward 2,000 years to about 1808, when the first real chemical science is being done, and there were 3 important laws. We'll describe each of these 3 important laws here in just a moment. We get the law of definite proportions, the law of conservation of mass, and the law of multiple proportions.
Law of definite proportions. A given compound will always be made of the same proportions of elements. Ethylene glycol is C2H6O2, always. Any sample of ethylene glycol will be 2 carbons, 6 hydrogens, and 2 oxygens.
And the way that we originally knew this was that it was always 51.56% oxygen, 38.70% carbon, and 9.74% hydrogen, because we didn't know anything about atoms at the time.
So if I have 20 grams of the ethylene glycol, I could multiply 20 grams by that 51.56 and figure out what mass of oxygen is it?
Seems reasonable, yeah.
Ooh, okay.
So 0.5156 times 20.
Yep.
Okay. Sodium chloride wound up is NaCl. It's 60.66% chlorine and 39.44% sodium. And it's always that. It's definitely always 60.66% chlorine and definitely always 39.44% sodium.
No matter how much the sample you have. If you have 1 gram or 2 grams or 3,000 grams, 60% of the sample will be chlorine, 39% will be sodium.
There we go.
That is the law of definite proportions.
And I definitely get that.
Good.
It's proportional. So the law of conservation of mass is actually a pretty cool one, and I think we're going to do this demo in class on Tuesday.
We're going to try.
We're going to do this one. But basically, this is a law that says that the mass of the reactants must equal the mass of the products. Basically, you cannot destroy any of the mass when you do a chemical reaction. So if you have a sealed up flask that you've got 2 different solutions in, and you make them react, you're going to wind up, if you here, you're going to wind up with the same mass after as you had before.
Law of multiple proportions. For elements that form multiple compounds, the ratio of masses of the second element will always come out as a ratio of small whole numbers. This is the third law of Dalton's, and it's technically the...
Mrs. G, this one just makes my head hurt.
I know, it's kind of the ugly cousin. We don't come across it much, but you really have to know the definition of it and that it exists.
John Dalton, and he's sitting there doing some thinking, just like good school teachers do.
Is he sitting in the pub?
Definitely not.
Well, looks like he's sitting at his desk.
In 1808, this guy John Dalton, who's an English school teacher, realizes that the Greek idea of atomos and these 3 laws can be combined together to actually form some sort of a theory about atoms. And that's exactly what he does. He actually makes his name by taking other people's stuff.
Does it?
Yeah, an English teacher.
Heavens.
Well, he's by saying he's an English school teacher, what we mean is he's British.
Oh,
Okay.
I thought you meant literally English.
So he's across the pond. He actually taught natural philosophy, which was in 1808 the code word for science. Natural philosophy.
Okay.
So what Dalton comes up with is he comes up with the fact that elements are one kind of atom. He comes up with the idea that compounds are made of 2 or more kinds of atoms, and
Only whole atoms can form compounds?
you can't split an atom in half is one of the things that and atoms are spherical and very small, and this is what his model actually talks about here. Along with his model, he comes up with 5 principles. The very first principle: all matter is made of small particles called atoms that can't be subdivided, created, or destroyed. So you got Democritus' idea right there in the first statement.
All atoms of an element have identical physical and chemical properties, and elements are made up of 1 atom, and those atoms have the same physical chemical properties. Okay, get it.
So yeah, 1 atom of gold is going to act like another atom of gold. So every atom of gold acts like an atom of gold.
Different types of elements are made of different types of atoms, so that makes sense. And a gold atom is not made up of silver atoms. It's either gold or silver, yeah? Is that what that's saying?
That's right. So there's different types of atoms.
So a sample of gold is all gold, and a sample of silver is all silver.
And a sample of gold atoms will look different than a sample of silver atoms.
Okay.
The actual atoms look different. I think that's one of the points here. Atoms are going to combine in simple whole number ratios to form compounds. There's the law of proportions there.
Okay.
And then in chemical reactions, atoms are combined, separated, or rearranged, but are never created, changed, or destroyed. So there's the law of conservation of mass.
Right.
Miss G, why are two of these red and 3 of these brown?
Well, I think, Mr. Kane, with the advent of technology and better equipment, I get the feeling some of Dalton's principles will not make it into the next century.
Now, the importance of Dalton's theory, since we know that parts of it are wrong, why is it that we talk about it? Well, it explains all the chemical data that existed at the time. He develops models of atoms, and this is actually a drawing out of his book of elements. And he actually shows his models are spherical, round spheres, and he actually comes up with some symbols for them, He's got things like lime and soda and potash, which I don't actually remember seeing those on the periodic table.
Some of his elements were not real elements, although some of them are.
But
I see phosphorus.
Yeah, and here's hydrogen, here's carbon and
Yeah.
oxygen and phosphorus. He's got a lot of good
completely
ones
wrong.
here. And he gave us proportions for molecules. So he came up with the idea that nitrogen dioxide, NO2, is always 1 nitrogen and 2 oxygen atoms. So we don't have to talk about it as percentages anymore.
Yeah.
We can now talk about it as atoms, because that was getting confusing. Sodium chloride is 66% sodium and 30 some odd percent.
Well, percent composition will be handy when the next couple of units.
We'll
but
see
for
that.
right now, it's just a 2-to-1 ratio.
It's amazing how things come back around. in
Everything
chemistry.
comes back around.
J.J. Thompson comes along. He's the next big scientist, and he's
Now, does this mean he's British?
he's an English physicist, so he studies physics in English. How about
Okay,
that?
all right, I'll go with that. I like that.
He wasn't studying the atom specifically. He was studying current. He was studying electricity.
Okay.
And he was using this device called the cathode ray tube. And if you look here, you can actually see that he's sitting next to his cathode ray tube, and you can see 2 wires coming off of it right here. Our cathode ray tube that we have in class doesn't quite look like that. It looks a little bit more like this. It's a glass tube. And what's inside of it?
It's a vacuum, isn't it?
Yeah, so a vacuum. What's
Meaning
inside of a
that
vacuum?
There's nothing.
Oh, yeah, no, that's right. So-
Empty.
all right, so it's empty on the inside. There's absolutely nothing on the inside here. And they call it a cathode ray tube because one end of it is called a cathode, and that's where they hook up the negative end of the battery. And the other end over here is called the anode, and that's where they hook up the positive end of the battery. Meanwhile, the inside is a vacuum tube, and it's got this nice little handy-dandy wooden stand so you don't electrocute yourself trying
Well,
to
if
hold it.
it's a vacuum, why do I see something?
Well, here, we should probably actually show this.
Oh, so there is something in there.
What that guy's bringing up here is a magnet.
It's bending away from the magnet.
So that light,
That green light. What is that green light?
well, if that's a magnet, that's not light.
Oh, but it looks like light.
It does look like light.
And
Let's
it's
see if we can
moving
get that.
away. Oh, now it's moving towards
Yeah. So
and away from.
depending on which side of the magnet we're holding there, will depend on which way it goes.
So that stuff is able to move, and it must have an opposite charge to the magnet. It's moving away from or towards, depending on the side of the magnet.
Right, because there's a law of electrostatics which say that opposites attract. So one of the things that Thomson concluded here,
The ray is not light. Light cannot be bent by magnets. So then what is it?
right? So he's saying that the ray must have some sort of a charge, and he thinks that he's actually got some part of an atom flying through, some sort of a metal atom. There's metal on the ends of those cathode ray tubes, so he thinks he's got some part of the metal flying through the vacuum.
So like particle rays?
Particle rays, exactly.
Oh, okay.
So he's got
charged particle rays.
yeah, and since it's reacting to the magnet, it's got to be charged because it's going away from the negative side of the magnet, but towards the positive side.
So that means it's a negative charge.
And that's
Wow.
the charges must be negative there. So he figures out also that they've got mass, and the way he does this, he comes up with a cathode ray tube that has a little paddle wheel on the inside. So it's got
Okay.
this little paddle wheel, and as this ray of particles comes across the paddle wheel, it actually starts moving the paddle wheel around.
Oh, okay, like a Ferris wheel.
Right. So there's another proof that it's not
around.
light, because light can't move.
Can't do that, yeah. All
A
right.
Ferris
So
wheel.
they're actually
Basically, what's happened here is Thomson's discovered something that's small, negative, and has mass, and he calls it the electron.
Dalton's model must not be right. The electrons seem to be much less massive than an atom. So in other words, Dalton who thought that smallest you could get, Thomson comes along and discovers that the electron's actually smaller than the atom. Thomson postulates if a negative electrons exist, then positive part of the atom must also exist.
We come up with what Thomson calls the plum pudding model. And if you're British, your mouth starts salivating when I say plum pudding.
What is plum pudding, Mr. Kane?
It's a dessert. It's kind of like we know what rice pudding is here in America. It would be like rice pudding with little
raisins?
bits of raisins in it.
Oh, I love rice pudding
Yeah.
with raisins.
Yeah. His model uses Dalton's atomic model to start off with. So his model of the atom is hard and spherical.
Okay, so modifications by Thomson is that the atoms are now divisible into smaller particles. He describes a large solid sphere which is positively charged. That's that nice little yellow sphere there. And interspersed in the yellow sphere are going to be the smaller spheres that are negatively charged. He technically has tiny spheres in one. Are the tiny little negative spheres evenly distributed throughout the large one?
They should.
So wait, now if that's true, then does that particle have a net charge if it's got positives and negatives in it?
Well, the whole thing, if we take a look at this entire thing as an atom, because there's positives and negatives equally distributed throughout, the whole charge of this is nothing.
Okay.
It neutralizes itself because there's an equal amount of positive charge and an equal amount of negative charge in the same area.
Oh.